Today we're going to consider this question, the first question on linear algebra out of Gunning's An Introduction to Analysis. It reads as follows. If W1, W2 are linear subspaces of a vector space V over field F, which of the following subsets of V are also linear subspaces in Y? And we're checking W1 intersect W2, W1 union W2, W1 except for W2, and W1 plus W2. Take up some seconds to try this out for yourself. Then I'll give you some hints, then we'll get on with the proof. Alrighty then, so for some hints, just try to remember what you need to show in order to prove that something's a linear subspace. In particular, you need to show that it's closed under addition and scalar multiplication, under vector addition and scalar multiplication, and that it has the zero vector. Alrighty then, let's begin with the proof. Let's start by proving which subsets are not linear subspaces. And to do that, let's show that 2 and 3 are not linear subspaces. W1 except for W2. This one's pretty easy, as we can just do this by counterexample. Let's suppose W1 equals V and W2 is some one-dimensional subspace. In particular, you might think about R2 except for some line, where W1 is R2 and W2 is the line going through the origin. We see that W1 except for the W2 will make it not a linear subspace because let's choose a vector V in this space W1 except for W2. This would need to be closed under scalar multiplication, but is not, because 0 V vector is equal to 0 vector is an element of W2, so it's not in our space we care about. Therefore, it's not closed under scalar multiplication, and we're done. For 2, we're also going to do a proof by counterexample, and let's again consider a subspace of R2. That's not right. Let me undo that. The way we do that is we take any two lines passing through the origin and pretend that these are neater lines than they are. And we see that these are not closed under scalar multiplication. Is if we take these two vectors and add them, for instance, if you take V1 from W1 and V2 from W2, and you add them, as long as one of them is, as long as they're not in 0, you see that they'll give you something that is in neither of the spaces. For instance, you can do this very explicitly to give a counterexample. With that, we have the entire, we've shown that both these are not linear subspaces because they're not closed under vector addition and scalar multiplication. So let's clear the board, and then we're going to try to prove that 1 and 4 are linear subspaces. We're going to start with 1. We're going to show that this is closed under scalar multiplication and vector addition. And we can also show that it includes the identity elements. The 0 vector, because 0 vector is in any subspace, therefore the 0 vector is clearly in this space. Next, let's let V be in this subspace of W1 intersect W2. Well, since it's in W1, for any alpha, alpha V is in W1, and alpha V is in W2 since it's in W2. Because V is in W2 and W2 is closed under scalar multiplication, alpha V is also in W2. Therefore, alpha V is in W1 and W2, so it's in their intersection. Therefore, we have closure under scalar multiplication. Next, let's choose any two vectors, V plus W, where V and W are taken from the intersection. Well, since V plus W are in the intersection, they're both in W1, therefore this is a W1. And for this one, for W2, we see that since V plus W is in the intersection, therefore, V and W are in the intersection, therefore V is in W2 and W is in W2. Therefore, their sum, since W2 is closed under vector addition, is inside. Since W2 is closed under vector addition, this is also in W2, but it's in W1 and W2, therefore it's in the intersection. So since we have the 0 vector closure under scalar multiplication and closure under vector addition, this is a linear subspace. Finally, let's show that W1 plus W2. So first, let's recall what this means. this is the set of all vectors V that can be written as W1 plus W2, where W1 and W2 are inside big W1 and big W2 respectively. Show this is a vector subspace, we need to show all the things we've shown before. In particular, let's check alpha V. By distributivity, this can be written as alpha W1 plus alpha W2. But we note that alpha W1 is in big W1 because big W1 is closed under scalar multiplication, and alpha W2 is in big W2 because big W2 is closed under scalar multiplication. Therefore, these are vectors from W1 and W2 respectively. Therefore, this sum is inside inside the vector space, inside the subset described by W1 plus W2. Therefore, alpha V is also in that because it's the same thing as this. Zero vector is clear because zero vector is in W1 and it's in W2, and zero vector plus zero vector is zero vector, so it's there. And now let's choose two vectors, V plus U, each of which have representations W1 plus W2. And then let's write the representations of U as Y1 plus Y2, where everything with index 1 is from big W1, everything with index 2 is from big W2. By the by the commutativity of vector addition, we can simply commute these, and we get that W1 plus Y1, this is equal to W1 plus Y1, plus W2 plus Y2. However, since W1 is closed under vector addition, we see that this is a vector in W1, and this is a vector in W2, so therefore V plus W can be written as a sum of something in W1 plus something in W2, therefore it's an element of W1 plus W2, because this is the set of all things that can be written as elements in W1 plus things in W2. With that, we've shown closure under vector addition and scalar multiplication, as well as inclusion of the zero vector. Therefore, we have shown that this is a vector subspace, as a linear subspace of our vector space V. Therefore, these are both both linear subspaces, and these are not linear subspaces. With that, we're done with the proof. Thank you for watching.